My dear students, let me welcome you all to a new edition of physics. In this edition, we'll learn about the transistor. We'll learn about types of transistor, action of the transistor, action of the transistor as a switch. Also, we'll be able to learn about logic gates, AND gate, OR gate, and NOT gate. So let's get started. The transistor. Okay, talking about types of the transistors. As a matter of fact, there are many types of transistors, but we'll focus on the bipolar junction transistors, denoted by PJT. Bipolar junction transistors. Okay, a bipolar junction transistor is made of three layers, three slices of semiconductors. These layers are called the emitter, denoted by capital E, the base, denoted by capital B, emitter denoted by capital E, and the collector denoted by C. Examples for such transistors. NPN transistor. What about it? It is a slice of P-type between two pieces of N-type semiconductors. Okay, so the base is made of P-type semiconductor. Meanwhile, the emitter and collector are N-type semiconductors. This was about, yes, NPN transistor, and it has got a symbol. It is in front of you, and there is something very important here. Okay. Direction of the current here, the arrow indicates the conventional direction. Once again, it indicates the conventional direction. Conventional direction of the current, it is the direction of the positive charges. Second type, it is PNP transistor. It is a slice of N-type, the base is made of N-type material between two pieces, two slices of P-type semiconductor. Okay, base is made of N-type, emitter and collector are P-typed semiconductors. And the symbol is shown in front of you right now. Okay, and do never forget the direction of the arrow indicates the, yes, conventional direction of the positive charges. Okay, we've got something to add here. Note, will you please? The arrow, as I said, the arrow of the emitter shows the direction of the conventional current. The base of the transistor is deliberately made very thin and lightly doped. It is very thin and lightly doped. Okay, in general, emitter current is equal to base current plus the collector current. IE equals IB plus IC. And now talking about the mode of work of the transistor, action of the transistor. Okay. The transistor or transistors act as fast switches, and they can act as amplifiers. So transistors act as fast switches and as amplifiers. Okay, in front of you we've got a circuit here. We've got a transistor, NPN transistor. E denotes emitter, C denotes the collector, it is quite clear that the base collector, your attention, base collector junction is reverse biased. It is reverse biased. So no current will flow. No current in this case will flow. Okay, no current can pass from the emitter, no electrons. Okay, since the base collector junction is reverse, yes, biased. But if we apply a positive potential, for example, positive 0.6 voltage, okay, on the base emitter, okay, a current, yes, electrons will flow from the N-type emitter across the junction in the P-type. Okay, in the region of the collector, they will be attracted by the positive plate of the 6-volt battery. Okay, this is quite clear. So we'll have, yes, a current that flows. In front of you, we've got the electronic current, electron flow. In this case, as I said, the emitter base junction is forward biased. In this case, we've got a current. Not all the electrons that cross the base reach the collector, because some of them combine with some holes in the base, but the recombination that occurs is very little, because the base is very thin and deliberately made, yes, very thin and light doped. That is to say, most of the electrons that have entered the base from the emitter quickly reach the collector. The loss of holes is made good by some holes that flow to the base from the base power supply. Thus, if IE is the emitter current, then alpha E is the fraction of the emitter current that reaches the collector. Yes, IE is equal to I base plus I collector. I base then is equal to I emitter minus I collector. I base equals I emitter minus alpha E I emitter. I emitter will be taken as a common factor, so the base current equals IE between two brackets 1 minus alpha E. If we regard the base current as the input current and collector current IC as the output current, a transistor acts as a switch in which base current turns on and controls the collector current. That's to say, if the base current is 0, no current flows through the base current, then collector current will be equal to 0. And when I base starts to flow, when the potential is about positive 0.6 voltage, potential across base emitter VBE is positive 0.6. I base starts to flow, thereafter I collector increases when the current of the base, yes, increases. The transistor can act as a current amplifier. How? Since IC, collector current, is much greater, IC, the output current, is much greater than the input current, I base, and a small change in the base current will cause a larger change in the collector current. So we've got a current gain. It is the ratio between emitter, it is the ratio between, yes, collector current to the base current. So it is equal to alpha E times emitter current over 1 minus alpha E between two brackets times emitter current. Of course, emitter current will be crossed out, so current gain equals alpha E over 1 minus alpha E. And now talking about the transistor as a switch, okay? Talking about the transistor function of the transistor as a switch. It serves as a switch, first a switch. So in front of you, we've got a circuit. In the shown circuit, of course, VCC, yes, it is equal. It is quite clear, it is equal to VCE. What is VCE? It is the voltage across the collector, emitter, and IC times RC, voltage across RC. Okay, it is quite clear now that the base is connected to a positive battery, so there will be a current in the base, and of course there will be a current in the collector. Okay, as I said, VCE is the potential across the emitter collector. Okay, and it is the V out. RC is the resistance in the collector circuit, and IC is the current passing through it. When connecting the input which is base emitter, to a suitable positive voltage, that is to say, the base voltage is positive, a current will pass through the base. High collector current will pass through RC. We said base current will, yes, control the collector current. So if there is a base in the current, so if there is a current flowing in the base, okay, high current will flow in the collector. There will be a high voltage, of course, across RC. The voltage will be nearly equal to VCC and low voltage from the resistor. Okay. The output voltage, VCE, will be so low. That is to say, when the base voltage is positive and suitable, the transistor is on. And now, when the base voltage is too small or negative, it is in front of you, the base is connected to the negative terminal of a cell, there will be, yes, no base current. There will be no base current, and only a very low collector current will flow. Okay, the voltage across RC will be very small, and the output voltage VCE will be, yes, high. That is to say, when the base voltage is too low or negative, the transistor is off. And the collector current is very small, so the output voltage on the collector emitter is high. And now talking about digital electronics. There are two types of electronics. As a matter of fact, there are two types of electronics. Analog electronics. In analog electronics, the information about a certain natural quantity, such as sound, image, heat, yes, is completely converted into an electric signal in the form of varying current or voltage. This was about analog electronics. And what about digital electronics? The information about a natural quantity is coded into a digital form. Codes used in digital system are decimal code, the binary code. Example for analog electronics, the way the image, we call it video, and the sound, we call it audio, is transmitted from a transmitter, and the way the image and sound are received at a receiver to operate a TV set. But example for digital electronics, your calculator is a digital form, a digital device. The processor in your calculator, which processes the data works with digital information. Also, your computer is an example for digital electronics. A computer can only execute instructions by counting with just 2 numbers at a time. The numbers are 0 and 1. And now, how to convert from decimal numbers to binary? This is very interesting and important. Conversion of decimal numbers to binary. For example, 43, we want to convert it into, yes, its binary equivalent. Okay, 43 is divided by 2. It will give 21, and remainder is 1. We'll do the same with 21. 21 divided by 2, it will be 10. 2 times 10, it is 20, remainder 1. 10 divided by 2, 5. No remainder, remainder equals 0. 5 divided by 2, it is 2, remainder 1. 2 divided by 2, 1, remainder 0. 1 divided by 2, we don't have anything, remainder 1. 1 does not include any 2's, so it will be 1 divided by 2, it will be, equal to 0, remainder 1. So the conversion is 1, 0, 1, 0, 1, 1. Okay, this is the binary, of the number mentioned in the example. The remainders from top to bottom form the binary equivalent, okay, from right to left. So, as I said, it is 1, 0, 1, 0, 1, 1. Note, if we want to mention the base in which a number is written, we write the base as a subscript next to the number. For example, 356 to the base 10 means 356 to the base 10. Okay? It is the decimal number. 1011, between two brackets, 2 means 1011 to the base of 2. It is binary. And now talking about the advantages of digital systems. Digital systems are very easy to design and build. Inputs and outputs are easy to join because they recognize the same voltage as logic levels 0 or 1. Information is very precise. Using the binary code, data can be composed only of zeros and ones. Information can be stored very easily. Information in the binary code, we call it bits, can be stored in silicon chips and on magnetic disks, each storing millions of bits. Digital circuits can be fully integrated. Whole circuits containing thousands of logic gates can be built on a single chip. Digital circuits can think faster. The simplicity of logic gates and their small size allows them to change their logic states very quickly. And now we've got an important give reason. Digital transmission is preferred to analog one. Yes, this is because digital coded pulses are very simple to transmit. They are either a 1 or 0. Unlike analog signals, which can only be amplified along with the noise, digital pulses can be very easily regenerated to their original form with no unwanted noise and no information is lost. In a digital system, it's only necessary to detect the presence or absence of a pulse. The shape of the pulse does not matter at all, as the information does not lie in the absolute value of the signal, but in the code 0 or 1. That is to say, it doesn't matter whether the pulse is contaminated with noise or not. What really matters is the state 0 or 1 itself. And now talking about logic gates. Logic gates are the circuits that perform logic operations. First of all, first gate is the NOT gate inverter. Talking about the NOT gate. Okay, this is the sample of the NOT gate. It is quite clear. It has one input and one output. Okay, the symbol is shown in front of you right now. What about the truth table? 1. Okay. It means the output in this case is the opposite. It will be 0. And if the input 0, the output is 1. And now, this was about the truth table of the, NOT gate. And in front of you, the electrical equivalent, we've got a lamp, a bulb, a switch connected in parallel, and battery. Right now, when the switch, is open, the bulb lights. Okay. So the figure shows an equivalent drawing for a NOT gate. Okay. When the switch is closed, the light goes off. Switch is closed means state of the switch is 1. State of the lamp is 0. It doesn't work. And once again, when the switch is closed, the lamp is off, and vice versa. When the switch, is open, the bulb lights. So once again, 1, this is the state of the switch, it is closed. Okay, the state of the bulb is 0. Okay, and if it is open, state of the switch is, open, 0. The lamp will be lighted, it is 1. So this was about the first logic gate, which is the, NOT gate. And we've got another gate, it is the AND gate. The sample is shown in front of you. It has got 2 inputs. It has 2 inputs and 1 output. As a matter of fact, it has 2 inputs or more and just 1 output. The symbol shown in front of you. This is the electrical equivalent of the AND gate. 2 switches connected in series to a bulb. For the bulb to light, the state of the 2 switches should be, 1 and 1. They should be, closed, so as the lamp light. So A stands for the first switch, B stands for the second. The output here is the lamp. 0, 0, of course. 0 means the switch is open, A is open, B open, no light. 0, A open, B open, no, B is closed right now, but the lamp will not be able to light, it is 0. And now A is closed, B open, also it won't be able to light, but it will be able to light when both of them are closed. Okay, so 1, 1, and 1. This was about the AND gate. And finally, the OR gate. The symbol is shown in front of you. It has 2 inputs or more and just 1 output. Once again, the symbol is in front of you, and the electrical equivalent of this gate, two switches connected in parallel, and the combination is connected in series to a bulb. Okay, just one switch is enough to light the bulb if it is closed. Okay, this is the OR state, OR gate. So A stands for the first switch, B the second. The output is the bulb. Yes. If A is open, switch is open, A, B open, so the bulb will not be able to light. A open, B closed. This is quite enough for the bulb to, yes, light. So we've got one. And what if A is closed, B is open? Also, this is enough to light the bulb. And of course, if both of them are closed, then we've got one. This was about the, yes, OR gate. And now talking about electronic circuits. Analog or digital electronic system is composed of electronic components connected together in a closed path called circuit. The components of the electronic circuit may be passive, as resistors, inductors. Inductors means inductive coils, of course you know this quite well. Capacitors or diodes, or they may be active, such as the active components are the transistors. And now talking about types of electronic circuits. There are two types of electronic circuits. Discrete circuits. So the first type is the discrete circuit. A discrete circuit is built up from separate components. Once again, a discrete circuit is built up from separate components. These components are connected together. The second type, yes, is integrated circuits. Integrated circuits, yes, IC or ICS indicates integrated circuits. What about integrated circuits? Integrated circuits are densely populated electronic circuits. So they are densely populated electronic circuits. What does it mean? It means it includes so many components which are much smaller, much cheaper to make, and much less likely to fail than circuits built from separate components. Integrated circuit, definition of the integrated circuit, it is the circuit that cramps, put all together, cramps all the required components onto a silicon wafer. It is the circuit that cramps all the required components onto a silicon wafer, where different regions are assigned to certain functions. In this way, we've come to the end of this edition. Until we meet again, my best wishes to you all. Thank you very much.